Working in the lab late one night, when my eyes beheld an eerie sight, for my monster from his slab began to rise, and suddenly, to my surprise,
he did the mash.
He did the monster mash.
The monster mash.
It was a graveyard smash.
He did the mash.
It caught on in a flash.
He did the mash.
He did the monster mash. From my love Notari in the castle east, to the master bedroom where the vampires feast. The ghouls all came.
Hi everybody. Hope you're having a good time. This chapter 9 has all been about scary things, so past kind of lectures have had like very scary themes, and maybe the last one was a little too scary with the Terminator, so I thought I'd have some fun with the Monster Mash song. And it's one of my favorite because it actually mentions the word lab in the very beginning of it. So thumbs up for that one. So in this brief 24A slideshow / lecture video, we're going to talk about E1 finally. Okay, and it is again in the same vein as you might think as SN1. Keeping those two in mind, they're very much at the end of our process as we try to determine what mechanism is taking place. So let's take a closer look at E1 today. And before we get into it, this was the slide with the practice problems from the last lecture video. And so I'm just curious, if you haven't tried them, please stop the video and try these. See if you get the same answers I do, which I'm about to show you right now. For the first one, it's imperative that if we spy this strong base, which is really what that is just OH minus swimming around in a bunch of water after it disassociates from the KOH. What you want to make sure is that your leaving group on your organic molecule in this chair, 6-membered ring chair conformation, is in the axial position. Remember our nice long name? We need it to be trans-diaxial paraplanar, anti, all of that, all in one name, trans-diaxial anti-paraplanar. So I want to make sure that this chloride is in the axial position. So that wedge coming out at you has to be an axial. And if you remember our little mnemonic about what happens to all the wedges as you go around the ring, they alternate. And so this methyl over here, this methyl would be equatorial, which means that this beta hydrogen is in a premium, beautiful spot as an axial beta hydrogen. And you want to look to the left and the right, just in case. And so this wedge hydrogen would be, if the chloride is a wedge axial, that hydrogen is a wedge equatorial, alternating as they go around the ring. This is boo hiss. Bad, bad, bad. Can't have an elimination reaction from a strong base, E2, without having my beta proton and my leaving group trans and diaxial. So this is why the only product that is formed from this with this little, oh, I also had this mnemonic, sorry. That's also supposed to help visualize this for you. But that means the only product I'm going to form is going to be this one alkene between the secondary carbon and this tertiary carbon with the beta anti-hydrogen. Okay? All right, let's try the next one. Next one has something a little odd. It still has the chloride in the axial position, and notice it's a dotted line. So I have to put the chloride in an axial position on my chair, which just means that this wedge H is equatorial. And if that wedge H is equatorial, it means this CH3, wedge H equatorial, next one over, this must be axial, which makes this beta proton equatorial. Boo, equatorial beta protons. Boo, bad news. So, look next door. And notice how I'm drawing in all the beta hydrogens. I highly recommend you do this anytime you spy a possible elimination reaction. And why is this a possible elimination reaction? I don't see any base present. There's no O- floating around. Ooh, something new, something cool that we introduced in the last video. Pure sodium metal. That's what this species is. Solid sodium metal. Very, very cool. And I put it with an alcohol. It happens to be T-butoxide. It's going to be formed because I put it with T-butyl alcohol. That's what the CH3 in parentheses 3 COH is. It is the conjugate acid of this cool looking alkoxide we have now. And the sodium metal is neutral to start with, and it almost exploded, caught on fire in the video as you saw. I love that video. Feel free to review it. And it will go and produce this negatively charged alkoxide. It is the only way you can get an H off an alcohol. Don't have your alcohols just throwing H plus into Wellesley campus tower. It just can't happen that way. Okay? So really, I am able to make my strong base now and start thinking about this as being a possible E2 reaction. It could be SN2 as well, but I look at where my leaving group's attached, and it's attached to a secondary carbon, a secondary aliphatic carbon to be specific. So no SN2 can happen here. Before SN2 can happen, E2 will take place. It'll go to the appropriate beta hydrogen. And we also learned that there's something special about this T-butoxide. It is bulky. It is big. And therefore, this T-butoxide here, I never even have to worry of it ever doing SN2. It will never do SN2. Only E2. Cool. That's great. So this is going to do an E2 elimination. It's going to try to find the less substituted beta hydrogen because it's so bulky. This is the Hoffman elimination. This is anti-Zaitsev. This is a Zaitsev beater. Hoffman. Okay. Now, do I have any other choice, Hoffman or Zaitsev, or which elimination is going to take place here? Let's take a peek. Remember, I had my beta hydrogen over here. I have an equatorial beta hydrogen, boo hiss, and one of these is going to be axial, one is going to be equatorial. So I have at least one beta hydrogen that is axial. So I still have my trans diaxial beta hydrogen to the leaving group on my chair, and this will cause an elimination to occur. So you will get 100% of this product. And you would get 100% of this product even if you used the KOH from the previous reaction. This is really nice. We like syntheses that only want to make one product. Nice and controlled. Sense of control. Not that we're control freaks. Yeah, I guess we're control freaks. We like control. Okay? Let's look at the last reaction. This one I had written in the previous video as number 1 and number 2, right on top of each other, 1 and 2. When it's written like that, what they mean is do reaction 1, as I'm showing you here, and show the product for reaction 1, as I'm going to show you here. And then take that product and do reaction number 2. Very important we follow that process. So again, here is another sodium metal and another alcohol. I must be trying to make the alkoxide and make my own very strong base. This is my ethoxide. Now, I have a really strong base, so it is also a good nucleophile. So it can do E2 or SN2. So keep looking at where the leaving group is attached. Primary aliphatic. It is not benzylic because that, even though that's a 6-membered ring, it's not a benzene ring with 3 double bonds around it. It's just an alkane ring with, somewhere way out there, a double bond, 1. So this is a primary aliphatic leaving group. And as we know, this is the only case where a really strong base can act like a nucleophile instead, because it's so unhindered, and pop on and kick off the chloride as a leaving group. Does that make sense? Good? Cool. So I write the product for this, and then I do step 2. And step 2 was the other unique piece of chemistry we showed you from the Sesame Street commercial break, so to speak, where hydrogen actually just adds across a double bond, chews up the double bonds, and makes every double bond disappear. I'd like to make sure we're clear about this. This does not work on benzene. So this only works on alkenes, not aromatics. And therefore, my double bond will disappear, and there are hydrogens added there in the place of those double bond, that double bond. And this is the way I was able to make this ether from this alkyl halide / alkene. So I have multiple functional groups on my starting material, and I was able to change them and turn them into really cool ethers. And that's the goal of Orgoland. Let's change our functional group. Okay, that was a lot. All right, let's get now to the business at hand, E1. And let's see what E1's got for us, okay? So E1 and E2 are really comparable to SN1, SN2. I hope that's not a surprise to you, because the naming is so similar. So here's a review of our E2 mechanism, where we have the strong base is needed. And the leaving group, we just digested this in huge detail over the last few video lectures. So let's take a peek at E1. Shouldn't be a surprise that if I start with an alkyl halide, I have a good leaving group, it's going to fall off and form a carbocation similar to SN1. So this is basically the same mechanism as SN1 at this point. Oops, here we go. Okay. I don't know if that came through or not. Here it comes. There you go. So it's the same mechanism as SN1. Slow step. Leaving group just has to fall off all on its own accord. Okay? Then a poor nucleophile could come and add to this and be an SN1. But what if you do a reaction where the nucleophile isn't really present? There maybe is no nucleophile. Or we'll find a way to make this next step more favored than SN1. But basically, you have a carbocation. This is very uncomfortable. And this molecule will do almost anything it can to get rid of it, to the point that it basically eats its own arm off. Oh my God! It just grabbed a pair of electrons from the beta carbon next to the carbocation and just ripped them in there. And in doing so, it casts away this hydrogen. Gets flung off as H+, with no electrons on it. But you know what? That's okay, right? That's okay. It's okay. Even though it's like, cannibalizing its own arm, it's thrown away an H+. And who would you rather be as a positive charge? Would you rather be a C+? Or an H+, which we've seen a lot of. So this is an E1 mechanism to produce an alkene, similar to producing an alkene in E2, but it just is slower. And notice in this E1 mechanism, there is no strong base. Okay? Let's go into a little more detail about stereochemistry, regiochemistry, and all the details that might involve E1 and how they're different from E2, if any. So this unimolecular reaction, because it's one step at a time, here's the rate law for it. This is kind of a review. But this is the part I want to get to now is I still want you guys to look at the carbon the leaving group's attached to and name it. Tertiary, aliphatic. This will help you decide if it's SN1, SN2, E1, E2, what mechanism it goes by. Now, in almost every reaction, you are always going to have a solvent of some kind. But this solvent could also act as the nucleophile. It's got a lone pair on it. Why not? Why can't this alcohol, which is dissolving this whole reaction process, act as the solvent to dissolve everybody, and being partially negative act as a nucleophile on a very bad situation, meaning SN1. So this could take place under an SN1 conditions, which means basically I'll leave nothing here. It might even be room temp. At room temperature, this is what would happen. You would not only get the SN1 product, but it would be your major product. And then a little cannibalization of the molecule eating its own bond beta to it to create this alkene would happen about 19%. Now, you don't need to know the percentages, but basically what it's saying is at this point, the SN1 is the major product. Okay? What if you wanted the E1 to be the major product? Not so hard. All you have to do is add heat. Lots and lots of heat. You reflux this. You boil this reaction in ethanol really hard. And if you boil it really hard, you actually change the major product to the alkene. So I will use a delta symbol when I want you to show me the E1 product is the major product, and I will remove the delta symbol if I want you to show me the SN1 is the major product. It's very subtle. Be on the lookout for this delta symbol, which represents heat. Okay? And the heat causes it to form E1. I could go through a long explanation of why this is favored. I don't ever want anything in organic land to be magic, but I'd have to start getting into Gibbs's free energy law. And that starts that phrase might just send you back to intro chem terror. And so instead, as I mentioned here, I've included it as a bonus slide at the very end of the pre-lecture slides that are posted on our Sakai site. So if you want to see the bonus slide and see why heat favors elimination over substitution, please take a peek. And it does this only for SN1E1. Okay? All right. Are there any other surprises like that that can happen with our E1 mechanism? The surprise being like, oh, I get SN1 too. Yeah, what other surprises are there? Well, how about this anti-coplanar transdiaxial? Do we have those concerns when we're playing around with an E1 mechanism? And the beauty of it is, no. But let me show you why. So first of all, I might be concerned that this leaving group, this bromide, is a wedge. And none of the beta hydrogens next to it that are drawn here as wedges and dotted lines, none of them are in the same plane as that wedge BR. You'd have to rotate it maybe to get it anti if you wanted to do E2 on this. But keep in mind, this is a tertiary carbon. And so it is very, very happy to just lose the bromide and become a tertiary carbocation. But if I don't have a strong base, I could do this E1 carbocation SN1 mechanism and just have the leaving group fall off and make this beautiful, stable tertiary carbocation. Okay? Now, to do the E1 mechanism, that carbocation is a new geometry. It's no longer tetrahedral. Notice there's no wedges and dotted lines. It's flat, planar. That means I have no rigid stereochemical constraints. Being flat, its p orbital here can rotate, move slightly, adjust here and there to match up with any bond of the CH3 sooner or later and allow this pair of electrons, oops, sorry, oh no, not end of show, no. Sorry. Allow this pair of electrons to fold in and bond with that carbon and create this beautiful pi bond. And all that has to happen here is this hydrogen again just flies off as H+. And this happens before maybe any solvent nucleophile can ever attack. Or if I do this reaction under heat, I'll get this elimination product. The end all be all though is, oops, sorry. The end all be all of this message though is that you do not need anti-coplanar beta hydrogens. What about Zaitsev's rule? Does Zaitsev's rule still apply in an E1 when I do this elimination? Well, notice again here, I have a beautiful tertiary carbon, an aliphatic tertiary carbon, in the presence of ethanol again, a very poor nucleophile. So it's not going to do SN2. It's a very poor base. It's not going to do E2. So the only thing this reaction has left to do is either SN1 or E1. So the leaving group can fall off, but notice in this problem, there's no delta symbol. There's no little triangle. So this must be room temperature, which is why the major product is the ether. And the minor products are these alkenes over here. But notice as soon as I start adding heat to this reaction, this is going to switch. And yes, E1 follows Zaitsev's rule. So even though I don't have to get a beta hydrogen aligned in transdiaxial and all of that, the more substituted alkene is the most stable alkene. It still follows the thermodynamic versus the kinetic. It still wants to make the more stable alkene. So notice this is a secondary carbon and this is a tertiary carbon versus a secondary carbon and a primary carbon. So if you have these choices of beta hydrogens to pull off, even in E1, try to make the more substituted alkene. Okay? Ooh, what about chairs? What if chairs go through this E1 process? Well, remember, transdiaxial paraplanar still apply. It didn't apply on any of these other ones. We didn't care where the p orbital was because we lost tetrahedral geometry. We became planar carbocation. And so in chairs, it's really important to recognize that in this experiment, again, I have, and definitely pause, it's a very busy reaction here. I blew it out with all the wedges and dotted lines. But if I have this reaction, notice I want this leaving group to be axial. I don't care. I don't care. Because look at what happens to it. It's gone. So it doesn't have to be axial anymore, and everybody else doesn't have to be transdiaxial. Because I have now a carbocation. Okay? And so now I have this carbocation, and so all I want to do is look at this tertiary versus this secondary. Which hydrogen, beta hydrogen, will be removed, cannibalized, eaten alive to form a double bond, the one on the top or the one on the bottom. So when you take a look at this, oh, let's see if it pops up here. Here we go. The major product is still going to follow Zaitsev's rule, even for a chair. And I'm going to try to form the more substituted alkene and not the less substituted. And in any problem for this situation, please, if I ask you only to draw the major product, this is the only compound I would expect you to draw. I'm showing you all the other ones. But if the question asks for the major product, please only show the one major organic product. That'll make your life a little easier. But if I ask you to show me all the possible products, then yes, I have to show both these two elimination products and even the substitution products. And I say products plural because that's a chiral center that leaving group is attached to. So in SN1, remember the racemic mixture? Yep, products plural could be racemic. Okay, so you could draw lots of products if you had to. All right, heady stuff. So for our next video class, let's see if you can tackle this problem. And it'll be the first slide, one of the first slides in our next video class, lecture 24B, which is coming up very soon. Okay, give this one a shot. See if you can show me the exact reaction mechanism with all the arrows needed to get from this starting material to this product. I hope you're having a good time. I miss you guys. I know Wellesley College misses you. And I hope you're doing well. Stay safe. Bye.